Okay, so here's going to be our next topic, and I don't even need my board. Honestly, all I need to use it for is to change slides. Because if you've looked at my notes, all the notes are is one slide of text and a whole bunch of pictures. I'm going to show you a bunch of diagrams or scenarios that will helpfully describe what Newton's first law is, and we're just going to talk about them. That's our class. Okay, so put the calculators away. We don't need them for this lesson, but we need to understand like the theory behind this law. So let me read it out to you first, because you guys can probably read it yourself. But here was Newton's law that he would have wrote about in his like paper that he wrote way back in the day. And this is one of three laws we're going to learn about. First law is this: when viewed in an inertial reference frame, an object either remains at rest or continues to move at a constant velocity unless acted upon by an external force. That is his law. And that is a lot of words that maybe don't mean anything to you right now. And so the reason why I'm doing this lesson this way is I'm going to keep going back to this slide after showing you some pictures, because you guys already know Newton's law, first law. You already do. You've seen it in action. You just didn't know this is what was happening. I'm going to go to a picture here. Here's a picture of an icy road. Very typical winter sort of scene. And the reason I picked this one right here is that the roads are so icy that I believe that these cars are trying to stop. And you can even see these tire tracks right here. The car is trying to stop, but it is unable to. Now, normally, what is the mechanism that stops a car? Let's walk back through it. It's friction, right? But let's walk through all the different steps. When you want to stop a car, what do you do as a person driving the vehicle? You move your foot, you put your foot on the brake. The brake ultimately activates a few different things, power steering, however that works, and it causes the wheels that are rotating, it causes a pad to like grasp it and prevent the wheels from moving anymore, right? So the wheels are no longer rotating. If the wheels stop rotating, then it's going to skid along the ground, and the friction between your tire and the ground will eventually slow you down. Does that make sense? Brakes from your foot causes the wheels to lock effectively, which you don't want in the wintertime if you know like safe driving skills. But your wheels effectively start to lock up. Because of that, the rubber tire and the asphalt road have friction, and friction slows you down. What happens if the roads are made out of ice? Your tires lock, your tires are no longer spinning, however, you're still moving forward due to a lack of friction. This is Newton's first law. You might not recognize it, but let me go back to that definition here. An object either remains at rest, I'm going to cover that one in a bit, so let's just put that in brackets for right now. An object continues to move at a constant velocity unless acted upon by an external force. What's the external force when you're trying to stop a car? The tires against the road, that friction. That's the external force. If there is no friction between the rubber of your tires and the asphalt road, there is no external force, which means that a car just keeps going. If you've ever been in a car accident in the wintertime, I've been in a couple before, it's not exactly the greatest feeling in the world when you're driving and you're trying to hit the brakes and you know your car is not coming to a stop. Hopefully there's no cars in front of you so you don't rear end them, because that's bad for your insurance. Hopefully you're not traveling too fast, because then you could actually get physically hurt, right? But you've probably all experienced this, even just a little bit, the idea on icy roads that like you're really not braking, and so therefore objects in motion stay in motion unless there's an external force. Does that make sense? So this is Newton's words. Objects in motion continue to move at a constant velocity unless there's an external force. That's what this diagram here helps us understand. Let me show you another one here. This is also Newton's first law. Also wintertime conditions. Here we have a person who has gotten high-centered. For some reason, they've gotten too much snow under the bottom of their car here. This guy right here is trying to push the car that way, and they can't. Well, this is also Newton's first law, only it's the first part of it. It's the part I put in brackets. It's the part where I said an object will remain at rest unless acted upon by an external force. Things that are stationary don't just randomly start moving. This calculator is sitting here on my desk right now. I don't expect it to just randomly start floating away because there's no external forces working on it. Objects that are stationary stay there, right? I mean, we kind of all recognize that. If I put something down and I walk away, I expect to be able to come back and find it there because nothing should have moved it. Right? And that's really what's going on in this picture here. This person is trying with all their might to push against the car, but apparently they just don't have enough external force to be able to get it going. So let me say Newton's first law one more time without it being on the screen. Newton's first law is objects in motion stay in motion, or objects at rest stay at rest unless an external force causes them to move. Objects in motion will keep moving unless you have a force to slow them down. Objects at rest stay at rest unless you have a force to get them going. Does that seem logical? Let me go to some more pictures here, because like I said, this is mostly just theory and understanding, and maybe you get it already, and I'm kind of wasting your time for the next 20 minutes, but let's try to go deeper. Here's a scenario, really classic example, where it's a tug-of-war. Are these two sides pulling against the rope? Clearly, right? I've even drawn a vector arrow here. The kids on this side might be pulling with 100 newtons of force. The kids on this side might be pulling with 100 newtons of force as well. Newton's law should really have one more word in it. I'm going to change Newton's law just slightly. We should really write it like this. Unless they're acted upon by a external net force. Net force is kind of a really important word here. Let me go back to our picture and just describe this again here. Are these kids pulling on the rope? Yeah. Are these kids pulling on the rope? Yeah. There are forces happening. But is there a net force? Well, no, because these kids are both pulling with equal amounts, and so the net force is really zero because they're pulling equally. Will these guys be able to move the rope if they're equally forced? Well, no, right? That's what I wrote down here. If your net force is zero, then you can't change the speed. You can't change the velocity of something. And so that's really important to keep in mind, is that there may be forces involved, but there has to be a net force involved. And I want to go back to the previous picture and talk about that for a second. Is this person right here applying a force? Yeah, of course they are. This person is clearly trying to push. Let's say that he has an applied force of 100 newtons. But why isn't the car moving? What force is opposing him? Yeah, the friction of all the snow that's underneath here, he can't oppose that. So friction is opposing him, and friction must be 100 newtons as well. And it has to be 100. It can't be 99 and it can't be 101. Because let's talk about that. Let's say that friction was only 99 newtons. Well, then the car would be moving, right? If friction was only 99 to this guy's 100, the car would actually move. It would take a while because you're only moving with 1 unit of force, but it would eventually get there. Let's say that friction by some miracle was 101 newtons and you were only pushing with 100 newtons. The car would be going backwards? That doesn't even make sense. There's actually a rule that says that like the force of friction always has to be less than or equal to your applied force. Because you can't have more friction than you're applying. Otherwise things would start going in reverse. Right? Like it wouldn't make sense for this car to all of a sudden, due to friction, all of a sudden start rolling over on top of this guy. It might because there's an incline, but that's due to gravity, not due to friction. Anyways, let me go back to this slide here. Hopefully I'm making my point. If we have two forces that are equal to each other, will anybody win this tug of war? No. You'll be stuck in perpetual, both just eternally fighting each other against like your evil doppelganger on the other side. You'll never win against that other person, because they're equally matched. I don't know, thinking comic books here. Let's try another picture here. Any of you guys play rugby or football, or you kind of know the concepts? Okay. I like this for anyone who's sports-minded. So let me just try to set the scene. You jump in if I'm doing it wrong, okay? But this is a rugby scrum. And effectively what's trying to happen is these players in white are trying to push the pile of players, say that way. But ultimately the players that are in blue are trying to push the pile the other direction. Is that probably a fair assumption in a picture like this? Right. Now let's say, just for the sake of argument, that all of these players collectively, they were all pushing with 1,000 newtons of force. Because they're all pushing collectively, right? But let's say that the other team was only pushing with 900 newtons of force. What would happen then? Yeah, you'd start pushing the pile, right? The pile would start to move this way a little bit. Does that make sense? Is that a fair way of describing this? Right, so a rugby scrum, the pile would start moving this way. And so all of a sudden, the whole mass of people start moving slowly in one direction, but they're making progress, right? I don't really care about the strategy of getting the ball out and doing other stuff, but if you get the concept, that's what's going on. There's going to be a little bit of motion in this direction. But here's a really cool thing then. Let's say that one more player, this guy back here, realizes, oh crap, they're starting to get moving here. I better come join the fray. And so one more player comes and joins, and now we're up to 1,000 newtons again. Here's a really cool thing though. The pile won't stop. The pile will actually stay in motion and keep going the same speed it was the whole time, just like the car on the icy roads. Because if you now have 1,000 newtons versus 1,000 newtons, now they're equal to each other. But if the object was already moving, it stays moving. And this is why sports athletes, in football and rugby especially, are usually coached to keep your legs moving. You guys ever get told that when you're playing sports? Keep the legs driving. Because what happens is, if all of these guys keep pushing and all of these guys keep pushing, but it was already moving, the pile keeps moving. Until this side over here manages to get up to 1,100 newtons, and then they can finally slow you back down to a stop. Okay? So it's actually a really cool principle that you can illustrate in sports. Football is great for this. Running backs in football are often told to keep their legs churning. So I'm going to try to diagram another scenario here. Say you have a running back in football, and the running back in football is holding the ball, and he was moving at, say, 3 meters per second. And all of a sudden, a big guy comes up and tackles him with 10 newtons of force. No, we need more than that. Let's go 100 newtons of force. But he has an offensive lineman behind him, one of his teammates, who decides to push him with 100 newtons of force. Well, what ends up happening is the pile keeps moving forward. And you can literally watch this happen in sports games where the person falls forward. I mean, they're eventually going to fall down because they can't keep their legs churning. But the pile will keep moving forward because if these two things balance each other, if it was already moving, it stays moving. Does that make sense at all? So you might have experienced this or seen this in a sporting event, but it is literally the same principle as the icy car. If something is moving, unless there is an unbalanced force, it just keeps moving. Let me give you another example of something like this that we don't see in everyday life, but is currently occurring. Earth is moving around the sun, right? Hopefully we all know that Earth is actually moving around our sun right now. Is Earth going to eventually slow down or stop? Well, no, because Earth is in motion currently. What forces would there be in outer space to slow us down? Is there friction in outer space? You know why there's no friction in outer space? Do you guys know the answer? There's no atmosphere. There's literally nothing out there. There is a vacuum in outer space. There is no friction in outer space to slow us down. And so Earth, in theory, is just going to keep going around the sun for forever. I mean, other things could come into play, like we could get hit by an asteroid, or the sun could change its temperature and its mass and turn into a red giant and stuff. But minus that, an object that's in motion stays in motion. Celestial bodies, like our stars and our asteroids and comets, they stay in motion because nothing is going to stop them. And they just keep going along their path for forever, just like the icy car, just like the rugby scrum. Okay, let's try another example. This one's kind of silly, but this is a picture of somebody probably in the Bahamas or somewhere really nice. I mean, look at the water. It is nice blue color, right? You got a nice hammock. This is sometimes a silly way of kind of describing Newton's first law, but this basically says an object at rest stays at rest unless an external force acts upon it. And so here's a person that's happy, they're at rest. Are they going to want to get out of their hammock? Not really. This morning my daughters had to get up and go to school. I had to wake them up. And they were at rest. And I had to shake them. Get out of bed. We got to go to school, right? Maybe you guys know the feeling. Only you're on the other end because you're the ones that want to stay asleep, right? But objects at rest like to stay at rest. Unless an external force, I'm pointing at myself here, unless a parent forces you out of bed, you might have just stayed in bed all day, right? Now, that's not really Newton's first law, but isn't it kind of the same idea? So I'm going to say this many times today because I want it to sink in. What is Newton's first law? Objects at rest remain at rest. Or objects that are moving continue to move unless there are forces that change things. Okay. Now, I haven't discussed this word yet. Now's as good a time as any. We actually have a name for this principle. It's called inertia. Inertia is the word we use to describe things that they like to keep doing what they're doing, basically. Okay? If you're at rest, you like to stay at rest. If you're moving, you like to keep moving. Right? And I mean, even people have these same tendencies. The word we use for that is inertia. Inertia is a property of things where they like to continue doing what they were doing. They don't just naturally change on their own. Does that make sense? This calculator right here is just going to keep sitting there. It's not going to naturally just change and like all of a sudden start walking away. Does that make sense? So that is a property I need you to know. And it really is, it's the resistance. This is a really good word to use. Resistance to change. You ever heard the word homeostasis? We've heard that word before in like other classes. Homeostasis, the desire to keep the same state. Stasis would refer to like the state that you're in. Homeo would be like the same, like homo is the same. So homeostasis refers to the desire to keep in the same state you're in. If I am in this hammock right here, I kind of don't want to leave. I want to stay there the whole time. So that kind of illustrates Newton's law. Let's keep going. Here's another picture. How does this illustrate Newton's law? Why are seatbelts so important? Because you don't fly forward out of your seat. Because you are driving in a car, or a little child is driving in a car. Therefore, you're moving. Let's say the car stops. Well, if you're not attached to the car, you're going to keep moving. Objects in motion stay in motion unless something stops them. And so if we don't wear seatbelts, if we don't have airbags, if we don't have restraints, objects that are moving will stay moving unless an external force, like say these seatbelt straps right here, unless there is the force of these seatbelt straps right here, kids would just go flying out of your seats if you stop your car too quickly. Here's another interesting one. This is called hammer throw. If you haven't seen this before, this is the sport where you take like a big chain and a ball on the end of it, and you spin it around in a circle. And I wanted to mention this now because we're going to spend a whole unit discussing something called circular motion. But this actually also involves Newton's law. There is actually a force in play right here. There's actually two. There is the force of tension on this chain right here. Because this chain has a lot of like pressure on it, right? Like this chain better not be made out of dental floss or it's going to snap, right? So this chain right here has tension on it. And one of the reasons why, guys, this chain has tension on it is due to a force that we're going to eventually talk about, which we abbreviate FC. You maybe have heard this word before. It's called, I need more space. I'm going to put it over here. Centripetal. Centripetal force is the word we use. And you probably have experience with centripetal force. The roundabouts that are out here. Maybe you have a friend or you yourself where you're supposed to go a little slower about the roundabouts, but you take them a little bit fast and like you kind of get thrown into the side of the door once in a while. Okay, you're smiling. You guys have seen this before, right? That would be centripetal force that you're feeling. You also feel this on like roller coasters. Anytime you start going into like a circular sort of motion, you feel like a little bit of like a motion towards the outside. And so that's actually what's happening right here is that this thing wants to go flying away, but it can't because it's attached to a rope. And this is a good way of illustrating Newton's law as well, because if the rope were to all of a sudden break, or you were to let go of it, this thing goes flying away, right? But due to Newton's first law, objects that are in motion are going to stay in motion unless there's an external force. There is a force. There's a force of tension. And the force of tension causes this thing to go in a circle. But as soon as tension gets broken, all of a sudden now it's going to go in a nice straight line, and you're now launching your hammer. Your, what do we call that thing again? Your hammer throw. Okay. So we're actually going to spend a whole unit discussing things that go around in circles. But one more quick recap, just in case you missed that. This object would want to keep going like in a nice straight line, but it's not able to because there is a force. There is a centripetal force caused by the tension, Ft, in this rope right here. And the tension keeps this thing going in circles. But as soon as we break that tension, now it goes in a straight line. As soon as we stop having an external force, Now it goes the same speed, and it now can go flying through the air. I'm almost done. I think this is my last slide. I put this slide in because if you guys don't remember, my last teaching job, I worked in Fort Macleod, very rural community, lots of farm kids there. This slide made so much sense to farm kids. And I don't know whether it makes as much sense to you guys, but let me try to describe it to you here. A lot of them, they would have cattle, they would have horses, and they'd want to like bring them places, but you have to put them in a trailer. Well, what's really important to someone who's driving a trailer is that even though you can drive fast, you don't want to. And the rationale is let's say you have to stomp on your brakes. Well, you're going to stop, the car is going to stop, the truck's going to stop, the trailer is going to stop, but what's going to happen to your horse? It keeps moving, right? Newton's first law, objects in motion stay in motion unless there's an external force. Well, the horses probably aren't tied down like how we put kids into car seats, right? And so the reason I brought this slide up here is that people who are driving horse trailers and stuff like that, they want to have a large distance in front of them so that they don't have to slam on the brakes. Even though the car might be able to handle slamming on the brakes, the animals in the back can't. Does that make sense? So that's what I've hopefully accomplished today. I've got about half an hour or so left. Let's just do a quick recap one more time about Newton's law, but hopefully you feel like you have a good understanding of it. Because there's no math to this. This is all understanding. Let me erase this and say it one more time here. Newton's first law. It basically is broken down into this. Objects that are at rest remain at rest. Or objects that are moving continue to move. Unless you have forces that cause them to. If you're sitting down, you're going to stay sitting until a force gets you up. If you're already moving, you're going to keep moving unless a force slows you down. That was Newton's first law. It's actually not overly groundbreaking. To be honest, I think my 6-year-old gets this. She just doesn't necessarily know the right vocabulary, and she can't put them together, but like, you guys knew about skidding through an intersection on ice, right? You've seen that before. You understand that this calculator is not going to start moving unless I push it, right? But now we have some words to put to it. So, okay, that's my lesson. Do you guys have any questions? Anything that comes to mind you want to ask right now? Okay, I'm going to stop the video here, and then I'll give you some last instructions. So video was 22 minutes, not bad.